Okay, so you got a function bound by three different functions. Y equals 4, that's a horizontal line. X equals 0, of course, that's your y-axis. And the line, or the equation 2y, it's going to be 2x equals y squared, which is really kind of the graph of a square root function, like that. Now, first things first, we're rotating it around the y-axis. That stuff has to be given to you. When we rotate around the y-axis, in what direction do I have to take my slice? Am I going to take a dx slice or a dy slice?
dy.
I got to vote for dy. I like that. Let's go with a dy. Your slice has to be perpendicular to your axis of rotation. So if you were going to do a disc or washer method, you'd have no choice. You'd have to set it up like this. So we got our one little slice there, like that. So, okay, looking good. And that slice is going to be a dy slice. Now, given that we're taking a slice like this, we rotate it around the axis, is this going to result in a disc or a washer?
Disc.
Got to vote for disc. Why a disc? Can someone tell me why this is going to be a disc?
Because there's not a gap.
Yeah. This area that I have shaded in yellow is flush. It's full up against your axis of rotation. So there's not a gap. So it's not a washer, it's a disc. So let's find the volume of one disc. Volume is going to be pi r squared times the thickness, or the height. What do you suppose the height is going to be in this particular case? Any guesses?
dy.
Yeah, height's going to be a dy. So let's draw ourselves a little disc. So there we go. There's our disc, aka hockey puck. And this distance right here, that's your thickness. That's that right there. So your height is going to be your dx, or I mean dy in this case. That's going to be dy. And then when you rotate this around, it's going to have some radius r. But the dy is a good place to start, because that tells me that r has to be some function of y. It has to be y equals something. So let's take a look at the radius. And the radius is going to be that dimension right there. That's going to be our r. Okay. When you're dealing with something horizontally, you want to calculate a distance, the radius is going to be right minus left. So the right-hand endpoint minus the left-hand endpoint. So, okay, how's that going to work? Well, if you're looking for a horizontal distance, you have to subtract things in the x direction. So if I had some general point here, it would have coordinates of x and y. And here, this would have coordinates of 0 and y. This would have coordinates of x and y. So it would be x minus 0 is what you get. Of course, that's not what we want, because I want something in terms of y. That's my variable. So I got to look up here and figure out, well, how am I going to express this in terms of y? In other words, how would you solve for y?
Square root of 2x.
Okay, yeah, that works. So, let's see. You know, I said I want to solve for y. My bad. And you gave me the exact right answer. I didn't ask the right question. we need to get x by itself.
Mm-hmm.
So x would equal,
Y squared divided by 2.
good. So y squared divided by 2 minus 0, or basically just y squared over 2. That's the radius. Let's plug that back in up here now. So that's going to be pi times y squared over 2 squared dy. That's going to give me pi times y to the 4th over 4 dy, or how about pi over 4 y to the 4th dy. Perfect. That's the volume of one disk. And again, that's my benchmark. I give partial credit for little things. Taking a dy slice, hey, there's some partial credit. Realizing that you're doing a disk and not a washer, partial credit. Getting this expression, more partial credit. Now the last little bit then is to finish it up and find the exact volume. So that would be integrating. Let's take the pi over 4 and put it out in front. Y to the 4th dy. But the big question is, what do I integrate to? And if you're curious, I'm kind of curious. I think that'd be the point 2 and 2 and 4. Let's see, what would it be? Y is 4, 16, 8. Yeah, 8 and 4. Pretty sure that's 8 and 4. It's 2 times 8 is 16, 4 squared is 16. So yeah, 8 and 4. But where do I integrate to?
0 to 4.
I got to vote from 0 to 4. Why 0 to 4 and why not 0 to 8? Somebody, go ahead.
Doing the dy, right? Not dx.
Good. We're integrating with respect to y. We want to see how y varies, and y can vary in this region, starting all the way down here at x equals 0, going all the way up here to x equals 4. So there's your limits of integration, 0 to 4. This is an easy one. I don't think I'm going to bust out the TI for this one. That's going to be pi over 4 times 0 to 4 of y to the 5th over 5. So that'd be pi over 4 times 4 to the 5th. Wait, let's see, 1,024. Bingo. 1,024 over 5 minus 0. These cancel, so it's going to leave me 256 pi over 4. No, over 5. Nice. So I wanted to get one in where we did a dy slice, just to let you know that you don't always have to take things, you don't always have to take a dx slice.
If you have time, could
Yes.
you do an example like dy, but like with a not a disk, like a washer type problem? Like at least what would that look like?
Sure, sure. How about if we take this one and instead of rotating around the y-axis, what if we rotate around the line x equal 8? That would be a washer. So, sure. Would that help? Would that be a good one?
Yes. We haven't. I don't think we've done that type, at least.
I think what he's meaning is to do like rotate around like y equals -1 or -2.
Sure. I mean, both of them would be fine. You want me to just go a little further and rotate around, you know, x equal -2?
Yep.
Okay. All right. Thank you. Let's try that one. Anything else on this one? Okay. So these are worth a lot of points. on an exam. And I would definitely make sure that you're comfortable with these things. Of course, Terry's going to be around for some more help. There's video help. So please do get some help. Let's think. All right, so let's do this. We got y equals 4, x equals 0, 2x equals y squared. But this time, rotate it around the line, x equal -3, for instance. That should work. All right, so I got to get busy and draw myself some graphs here. Let's use this one. Here. And want my region again. I think I want to give myself a little bit more room here in the x direction. Let's shade this in. So we're using the same region. We're just rotating around a different line. I want to see what effect that makes on our volume and on the setup. Of course, the setup is the biggest part of this. This point is again going to be 8 and 4. This time we're rotating around the line x equals -2. So we're rotating around here.
It wouldn't be -3.
Oh, pardon me, -3. There we go. Beautiful. So grading these things is a challenge, and what I've realized over the years is you've got to set up little hurdles. Like, okay, you get the first part, okay, that's some points. You get the second part, that's some more points. So even if you don't get this completely right, I encourage you, I implore you to try and get the setup right, all right? And try and get as much of it as possible. The first hurdle is this. Is this going to be a disc or washer?
Washer.
Got to vote for washer. Anyone else? Is she right?
Washer, yep.
Yeah, because there's a gap. This region doesn't touch flushly against your axis for rotation, so it's a washer, not a disc. What kind of a slice am I going to take? dx or dy?
dy.
dy. It's dictated, right? There's only one direction that's perpendicular to your axis of rotation, and it's this one right here. So you have to take a dy slice. There's no choice about it. So if I told you to do this one by a washer and you did a dx slice, I probably wouldn't grade much more because the rest of it would just be wrong. So this is going to be our dy slice. And I know I'm going to set up a washer. So let's find the volume of one washer. And it's helpful if you actually write that down for me, because as I scan your paper to try and give you as much partial credit as I can, you know, that kind of stuff helps. So I'm going to continue to kind of draw these things a little bit. Somebody asked me earlier, you don't have to. So there we go. And let's draw in this here. So that's what's going to happen. This is going to wrap itself around this axis. And when we do that, you're going to get these two cylinders here. You're going to have an inner radius and an outer radius. Where my implements of destruction go? So we'll do here and here, R1 and R2, inner and outer radius. Do you remember the shortcut that I gave you for the volume formula? Volume of one washer.
I times R2 minus R1, D, I guess it would be dy.
Good. Both of those have to be squared though. So yeah. Perfect, thank you. So pi times R2 squared minus R1 squared times the thickness, which is your dy. So it's just a matter of figuring out your thicknesses. I need an R2 and an R1. Now because we're doing things in a dy slice, instead of top minus bottom, what do I gotta calculate?
Right minus left.
Perfect, right minus left. All right, so let's put a few points on everything. I'll start with a general point, x, y here. But when I move over to the y-axis, my point becomes 0 on y. And when I move over here even further, it becomes -3 on y. And the reason I put those there is just to help me figure out, you know, my radii. I've got an inner radius here. Let's see. Where should I want to do it? Yeah, I guess I'll do it this way. So it's going to be R1 is the distance between those two. And then the distance between these two, that's going to be R2. That's going to be my outer radius. So I need expressions for those. Let's start with R2, the outer radius. R2 is going to be right minus left. Now, we took a lot of time setting this up, drawing a careful diagram, and it's going to pay off. Right minus left is going to be pretty easy. It's going to be x minus what? Well, I need to deal with the difference in the x
3.
coordinates. X minus -3.
Plus 3.
Good, so it becomes x plus 3. But this dy here tells me that, wait a minute, I got to get rid of that x. Instead of an x, I got to have an expression in y. So what's that expression in y going to look like? Well, you can solve for x back up here at the top and get x equals y squared over 2. So my final expression for R2 is going to be y squared over 2 plus 3. That's what I needed. That's going to go in here. Okay. Are you comfortable with that part? I mean, the setting these things up is the hard part. That's why a lot of times on these types of problems, I'll say, okay, finish it up with numerical integration. That is, do fn int off your calculator. Because by the time you get to that expression, you're exhausted, and the last thing you want to do is try and find an integral. Are you comfortable here?
Yes.
Thank you. All right. How about R1? Can anyone tell me what that's going to be?
-3.
Well, let's take and do it just like we did here. Do right minus left.
Just 0 minus -3 then?
All right, 0 minus -3. And what happens to 0 minus -3?
+3.
+3. Perfect. So that's this one. So I've got expressions for both of these. Let's put them in there, and we'll almost be done. So it's going to be pi times all that dy. It's going to be y squared over 2 plus 3 squared minus 3 squared. Again, it's better to simplify things here than it is to simplify it in your integrand. So let's make this as simplified as possible. I'm trusting that I don't need to square this out like I did in the last video by hand. So let me just help us out here. That's going to be y to the 4th over 4 plus 3y squared plus 9 minus 9. Okay, looks good. But there's a little bit that I can do here to make my life even easier. I can cancel out the 9s. So the final expression that I get would be pi times y to the 4th over 4 plus 3y squared dy. And that is worth a lot of points right there, getting that far. How are we looking with this expression? So far, so good, or can I back up a
Good.
step and help you out? All right. Let's finish it up. To finish it up, I need to add up all such possible disk, or washers, I should say. And that would start at 0 and go up to 4. So I'll take the pi out in front, the integral from 0 to 4 of y to the 4th over 4 plus 3y squared dy. I don't think doing this is going to be terribly enlightening. That is finding an antiderivative and working with all the arithmetic. So let me just take a little shortcut here. And if I tell you to do it with numerical integration to finish up, hey, go ahead, do it with numerical integration. So that's going to be from 0 to 4 of 1/4 y to the 4th. So I'll put that in this way. I'll put it in 0.25, which is the same thing as 1/4. We use x's as opposed to y's. Oops, guess I was using this to teach trig. So I got things in polar form. X raised to the 4th plus, oops, x to the exponent plus 3x squared dx. Now leave the pi out, because if you put pi in, it's not going to be able to do this trick for you. Not going to be able to turn it into a fraction. So for instance, if I had pi times this, for instance, I'll get the right decimal answer, but there's no way that I'd ever figure out that it's 576 over 5, you know, because when you hit the math key, answer the fraction, you get nothing. But if you did 576 pi, oops, not e, pi, divided by 5, it should match that perfectly. So you can check yourself like that. if you put in the pi, but if you really want to get the nice exact expression, leave the pi out. Okay, that took a little longer than I expected, but I think it's time well spent. Are you guys feeling better about solids of revolution?
Yes.
That's the answer I wanted to hear. Is that a sincere answer?
Yes, it
I'm kidding.
is.
All right, that's good. Thank you. All right, let's take another break. We'll come back and do a problem or two from section 6.5, and then we'll wrap things up.